start off today, we're going to discuss a very important eclipse observation that happened more than 150 years ago. Back in 1859, an important instrument called a spectroscope was invented by two scientists named Bunsen and Kirchhoff. And this really revolutionized how people could see and observe and understand the nature of light. So a spectrograph is very similar in how it works to a prism. You shine light through it, and the spectrograph, or the prism, breaks up the light into its different components. Now when we shine visible light through a prism, it breaks up the white light that we shine through into all of the different colours of the rainbow. And so we're able to observe red and green and blue and purple and all of the different elements. But that can be done outside of the visible wavelength as well. Scientists use spectrographs because they can be used to pull out some really fine detail in the spectrum that is being analysed. When we look at the spectrum of light, we generally see this as a series of peaks and troughs, but lots and lots of squiggly lines, and each one of those lines is a signature of a specific type of atom or molecule or ion. So that is like a fingerprint of a particular element, and that means that we know that that element is present in the material that's emitting the light. So if we look at the spectrum coming from the sun, we can study the fingerprints coming from the sun, and we can tell which components, which elements are in there. And not only that, but we can tell how much of those elements are in there as well. The defining moment in solar spectroscopy happened in 1869, so just 10 years after the invention of the spectroscope. There was a total solar eclipse that two independent scientists, Young and Harkness, both used spectroscopes to observe. And during that total solar eclipse, both Young and Harkness independently observed a type of light that had never been observed on the Earth before. This spectral line appeared in the green part of the spectrum, and scientists had no idea what generated this line. They had never observed anything at this particular wavelength before, and therefore they made the presumption that this was an element that only existed in the sun's corona, and therefore they called it coronium. So the presumption was that we had an element that had never been observed on Earth, therefore it didn't exist on Earth, and therefore it was an element found in the sun only, actually in the sun's corona specifically. It wasn't until more than 60 years later, in the 1930s, that a Swedish scientist named Edlund proposed that this wasn't in fact a brand new element, but that it was a very, very highly ionized form of iron. In fact, he proposed that of iron's 26 electrons, that 13 of them had been removed in order to produce emission at this particular wavelength. Now initially this seemed like a very far-fetched idea. In order to remove 13 electrons from iron, that requires a huge amount of energy. So when we talk about energy, we can talk similarly about temperature. If you have a lot of energy, you can calculate what the temperature must be at that location. In order to produce iron with 13 of its electrons missing, we call that iron 14 in astronomy, that requires temperatures of more than 1 million degrees Kelvin. Now, one of the main reasons that scientists were skeptical about this is that the sun's surface is only 5,000 to 6,000 degrees Kelvin. And now we're talking about the upper layers of the atmosphere being at more than 1 million degrees Kelvin. So where's all of that energy coming from? And you know, that's something that we still don't have a solid answer for. Although scientists continue to investigate and produce theories, there is no widely accepted answer to why the sun's corona is more than 1 million degrees temperature. Although we have confirmed that what was once considered coronium is actually highly ionized iron, we don't know how the temperature in the corona is getting to be so high. And this is the solar coronal heating problem, and it's one of the great unanswered questions in solar physics. So this just goes to show that even 150 years later, observations that started with a solar eclipse still have no answer. This year, the eclipse is particularly important because normally when we have a solar eclipse, we get about 2 minutes of totality. However, we're able to track this eclipse across the entire country, and that means that we can get almost 90 minutes of solar totality. Who knows what kind of questions our observations in August of this year will produce, hopefully pushing the field of solar physics further into the future the same way as the 1869 solar eclipse did. If you have any questions or comments, please feel free to post them below. If you have anything specific that you'd like us to cover in one of our webcasts, please get in touch with us. You can email us directly at outreach@nso.edu. You can post your suggestions below the videos. You can get us on Twitter at @NatSolarObs or on Facebook at facebook.com/National Solar Observatory. And we have a new Instagram account, and our Instagram handle is @National Solar Observatory. So please get in touch, let us know what you think of the videos, if you have any questions, if you'd like us to cover anything specific, and we hope that you'll join us next month.